Recording has started.
Alright, let's move on. So let's look at some examples. So I received your feedback, and some of you suggest that we have more examples during the lecture, so I will do that. So here, this is just a simple example to practice the IV equations. And here we consider a process technology, which is a minimal L is 0.4 micrometer, and the TOX is 8 nanometer, and the mobility is this 450, and the threshold is 0.7. So first, find the COX and the Kn prime. So let's do that. So you know the COX, as we just discussed, is this epsilon OX divided by TOX, and that is epsilon 0 and epsilon relative, and then TOX. So epsilon 0 is the vacuum permittivity, and it's a constant. You can find this number, for example, from your equations in the exam we provided in the last page. There is a physical constants. So this one is and then the epsilon relative, this is the dielectric constant. For the silicon dioxide, SiO2, this one is 4, and actually to be more accurate, it's 3.9. And then divided by the TOX, in this case is 8 nanometer, and we have to convert the unit from the nanometer to centimeter. So you know it's 10 to minus 7 centimeter for 1 nanometer. So here we want to use the centimeter for the length unit, as we discussed. So if you do the calculation, you will get this 4.32 times 10 to the power 7, negative minus 7 bar per centimeter squared. And then what is Kn? Kn by definition is mu n COX. So just plug in the number mu n here is 450, and times this number 10 to the power negative. So here, because we already convert to centimeter square, so those centimeter square will be cancelled. So you will directly get this Faraday over Vs, and it's the same as, say, it's this 1.94 times 10 to minus 4 ampere per volt square. So this is the Kn prime, and then the next question is if the MOSFET has this W over L like this, 8 over 0.8, then calculate the voltages you need to operate the transistor in the saturation with the current 100 microamp. So basically here we ask you how to design the voltage to give you 100 microamp from this transistor. And it's in the saturation, so we should use the saturation current equation. So that is ID over so it's always write down the equation first in your homework or in the exam. So this is to allow you to get partial credit. And so we do that first. Here write down the correct equation because it's in the saturation. So we use this one. So here we ask what is the voltage you need to apply. So by definition, this is the same as this VOV squared because we define the VGS minus VT as the VOV. Now you can plug in the numbers. So here ID 100 microamp unit and the other side is this half times this number. If you convert to the micro, it's 194 micro. And then the W over L here is 8 divided by 0.8. And then this VOV square. So you can solve for the VOV. So you can move the values to the other side. And you can solve for the VOA. I will skip that. So the VOV will be 0.32 volts. Of course, you will have two solutions for this second order equation. One is positive 0.32, one is negative. And you know it will always be positive because VGS minus VT needs to be larger than 0 to turn on the transistor. So this must be positive. So you will have the VGS is 0.32 plus the VT. VT here is 0.7. So you get the 1.02 volts. So you need to apply gate voltage 1.2 volts to give you 100 microamp. Okay, so then the third one is to find the voltages to operate this device as 1000 ohm resistor for very small VDS. So this is to approximate the transistor as a resistor. So that means the transistor is in the linear region, and then we can use the equation for the resistor, channel resistance in the linear region. So this is in the saturation region, and the third one is in the linear region. So in the linear region, if you recall here, we say that if the VD is very small, then the transistor has a resistance of the channel like this, 1 over mu n COX W over L VOV. So you write down that first. 1 over mu n COX is your km per run here. W over L VOV. And then you can plug in the number. You have 1000 ohm, and then 1 over km per run is what you have here. Is this 1.94 times 10 to negative 4. W over L is still your 8 over 0.8, and then VOV. So you can solve for the VOV. So that is 0.52. And similarly, the VG will be this 0.52 plus the threshold. So will be 1.32 volts. And now the VD needs to be very small. The VD needs to be smaller than this VOV to be in the linear region. So this VD should be much smaller than this 0.52 volts to satisfy the condition for the third one. So any questions on this example? Okay, and the rest is just the solution. So I did it for the derivation for live here, but I actually have the solution prepared already here. Okay, so then let's look at the second order effects. So this is the second order. So when we talk about the first order effects, then we are going to apply those equations here. So this is the first order. We only consider the equations like this. And in the second order consideration, so we are going to look at the saturation region, no longer saturated. So if you look at the ID versus VD in the practical transistor we measure today, you will see that the drain current, even in the saturation region, will increase with the drain voltage, no longer flat. So we can explain this effect by this channel length modulation. So what is that? So if you look at the source, channel, and the drain, and then this is the channel with those electrons. And we talk about the pinch-off point. So we say that at the VD set here, we're going to have this pinch-off. This is when the VD equals to this VGS minus VT. But now if you further increase VD, the electrons will move faster and faster because the natural field will be larger. So the electrons in this region will be easily swept out from the channel. So that means in this whole region, then the electron density will drop to 0. So it's like the pinch-off point is moving towards the left here if you further increase the VD. So it's like this pinch-off point is moving towards the left. Or in other words, the effective channel length is reduced by this delta L. If this distance here is delta L, then the effective channel length will be this L minus delta L. So it's like channel length is modulated. So this is the channel length modulation effect. So if the channel becomes shorter, then from the IV equation we derived before, you know it will become larger. Why is that? Let's ignore this part for now. So if you only look at what we show here, this is the same as the square law in the first order equation, right? And then if you say if the channel become smaller, then the L becomes smaller, the current will become larger. So this is this channel length modulation effect. So to quantify this effect, then we add this multiplication here towards the saturation current equation, this square law. And this 1 is just the square law itself, but we need to add a small number, small term to correct this modulation effect. So we add this lambda times the VDS. So this lambda is just coefficient. And then we want to show that the drain current increase with the VDS. So here we no longer change the L, because L, if you only consider the source to the drain distance L, we don't change that. Equivalently, we think the current will increase with the VDS with this coefficient lambda. And then this can accurately describe this IDVD plot in this region. So here we have multiple curves because we have different VGS. If we change the gate voltage, if we increase the gate voltage, then we have larger current. So we have different curves here according to different VG, the gate voltage. But what you can do here is to trace back the straight line towards the negative side. Then all the curves here will merge to one point. And this point, we call it early voltage, and we call it VA. And this is actually 1 over lambda. If you look at the early voltage VA, is 1 over lambda. This is given by this equation. If you want the current goes to 0, right? So here, this is when the current goes back to 0. So if this current goes back to 0, that means it's 1 plus lambda VDS goes to 0. This term is to be 0. Then the V will be 1 over lambda negative. So that's why we have this VA 1 over lambda. This VDS is this negative VA here. So this is a second order effect, and I want to make a clarification here. So in this course, if we don't specify in the homework or exam, then we don't consider this channel length modulation effect. Of course, if we specify that you need to consider that, then you do need to use this equation. But if we don't say anything, then you just use the first order equations as we showed before here. If we don't specify, by default, you use this one. But if we say you need to consider this one, then you use this equation. The reason is that in the digital circuit, this channel length modulation effect does not matter too much. So because we are going to learn that in the next couple of slides, for example, in the digital inverter, then when we turn on the current, turn on the transistor, we only care about the transistor is on or off. So then we don't really look into the exact solution for the currents. But this approximation may not be true for the analog circuit designer, because analog circuit designer actually really look into this slope of the transistor. And this is called the small signal output resistance, RO, for the analog designer. If you design the, for example, the voltage amplifier, you want to amplify small signal sinusoidal wave to a large signal sinusoidal wave, then the transistor gain, the voltage gain, depends on this slope. So here we're not going to discuss the details of the analog circuit design. There is a separate course on that. But for the digital computers, for the digital circuit, here we focus on the first order equations. All right, any questions here? One question here, if there's no electron between the modulated channel and the drain, why does the current still flow? Okay, this is a very good question. You are referring to here, okay. So this is a simplified physical picture to talk about the pinch-off point moving to the left. Of course, this is not true in the reality. So here, if you follow the physical picture here, seeing the pinch-off is moving towards here, then there's no carrier here. Okay. In reality, of course carrier will be flowing here because you need to pass the current, right? So in this simplified model, here the assumption is that the carrier here, the electrons, move so fast. Okay, once it reaches to this point, it immediately swept into the drain. Or in other words, here the assumption is that the velocity of the electron approach infinity. Then once the electron gets here, then it's swept to the drain immediately. That means the velocity is like infinity. This relates back to the discussions we have here. If you recall, we say that the current needs to be continuous. So as you get smaller and smaller charge density in the channel, then they will move faster and faster. So if the charge density goes to 0, that means here it will be infinity. Otherwise, you cannot get a constant product here. Of course, this is not true in the real device. This is just the simplification of the physical picture here. So in reality, the electrons will move there through that, but it's very fast. So to some extent, we think, okay, the electron density goes to 0 and the velocity is very fast. But it's not true. I mean, in the real physical picture. Mathematically here, because we use simple equations, then we have those conclusions. But in physics, it's not true. This is because we use simple equations here. So does this answer your question? All right. So then let's move on. So here, let's look at one example to determine the bias point of this circuit. So here you have some resistor and you have one transistor here. So the transistor's parameters are given, like the threshold voltage is like 1 volt, and then this Kn, this actually is a Kn, is 1 milliamp per volt square, and then neglect the channel length modulation. So here the question asks you to determine all the voltage nodes. So basically asks you what is the Vg, and here you have Vd, and here you have Vs. Ask what are the voltages here, and what is the current ID. So how do we approach this one? So all the resistance are given, and the VDD power supply is 10 volts. Then what is those voltages? So of course, here we look at the left branch. This one is easy, right? So here you only have 2 resistors, and the gate, there's no current flowing into the gate of the transistor because this is a cap, and then it's like an open circuit. So the gate has no current flow between source and the drain. So here then you only have the resistor divider, right? And then you have 10 volt here. So these two are the same. So then this is 5 volts. The Vg is 5 volts. And then the current, of course, will be 10 volt divided by, in total, 20 mega ohm. So then it's 0.5 micron. So this is easy. So what is difficult here is the transistors branch. So here, the gate voltage 5 volts is known, but you don't know the Vs, and you don't know what is Vd. So basically, you don't know the transistor's operation region is triode or it's saturation. You don't know. Why you don't know? Because you need to determine the VGS minus VT compared to the VDS. And the VGS actually is VG minus Vs, right? And VDS is VD minus VS. And VG, this is known, 5. And VS, you don't know. VT, given, 1. VD, you don't know. VS, you don't know. So look at those, you don't know which one is larger, which one is smaller. So then this is tricky. So how do we do here? So we have to assume, okay, the transistor is either in the saturation or the triode, because there are only two possibilities here. We have to assume one, and then later we can verify whether our assumption is correct or not. So let's assume the transistor is in the saturation, okay? If the transistor is in the saturation, we can use the saturation current equation. So that is ID equals to this Kn, and then VGS minus VT squared. Right, this Kn is this mu1 COX W over L. So here we just plug in the symbols for the Vs and Vd. So what is this VGS minus VT? We already say that is 5 minus Vs minus 1. So for this one. But we don't know what is Vs. But we can represent Vs using the ID. Why is that? Because here this Vs, you see, is the current flow ID multiplied by the resistance 6 kilo ohm. So if you think this is Rs, this is Rd, the drain source side resistance and drain side resistance. So actually your Vs is ID Rs, is the voltage drop on the resistor Rs. And the drain side Vd is the VDD power supply minus the voltage drop across this Rd, right? It's ID Rd. So here, let's say if we plug in the number, Rs is 6 kilo ohm, so let's use 6 for now. And we know the unit is kilo. That means the current will be in milli. Milli times kilo, is 1. So here, let's use 6 ID here, represents the Vs. The 6 is 6 kilo ohm. And then the Vd is your 10 volts minus ID times also here 6 kilo ohm, 6 ID. So you can plug in this Vs and Vd, especially this Vs, back to this equation, this current equation for the saturation. So you have ID equals to Kn. Kn is 1. So it's 1. And the VGS minus VT. So this is here VGS minus VT. So we have this 5 volts, that is Vg minus Vs. Vs, what is Vs? Vs is here we represent as 6 ID. And then Vt is 1 volt given. So you see here you have this equation, and you can rearrange the terms because this is a second order equation. You have ID. Only unknown is ID. So you need to solve for ID. So if you do that, you can rearrange the terms. Actually, it's 18 ID square minus 25 ID plus 8. So basically, you make it like ax squared plus bx plus c equals to 0, your second order equation. And I believe you know how to solve this from your high school math. So there are two solutions. One is ID equals to 0.89, and here the unit will be million because here we use kilo ohm. So 6 kilo ohm times some million will give you the volts. So one is ID 0.89, the other is ID 0.5. So which one is real? You have two numbers, but the circuit cannot have two currents at the same time. So one of that is invalid. So let's verify that. How we need to verify, because here you can plug in the ID back for the VS. So for example, here if ID is this one, you back calculate what is VS. VS is 6 ID. 6 times this one is 5.34 volts. Then you will see that this is invalid because VS is 5.3 and VG is 5. So your VS is larger than VG. That means the transistor is in the cutoff, right? So this is cutoff. Your VGS is negative, so you cannot turn on the transistor. So this is not true because you assume the transistor in the saturation. But here, if you verify that, it's actually in the cutoff. So this assumption is not good. So this solution should be discarded. And then for this one, you can verify that this VS will be 3 volts. And then the VD will be here 10 minus 6 times 0.5, basically 3. 10 minus 3 is 7 volts. So basically here you have 3 volt here and 7 volt here and 5 volt to the gate. So you can verify that VGS is this 5 minus 3 is 2 volts. And VGS minus VT is 2 volt minus 1 volt is 1 volt. And VDS is 7 minus 3. So it's 4 volts. So this one, 4 volt larger than this VGS minus VT. This indeed is in the saturation. So here you will get this solution. This is valid. The circuit will only have one valid solution. If you start with a linear region assumption, you will also reach some values for the ID, but later if you verify that, it will be invalid. So any questions here? And let's spend one more minute on the second question. So here it asks, there's no second question for this one, I think. Okay, I think that's it for this one. Yeah, so that's it. So time is up, and any final questions before we stop here today? If no, then that's it. Thank you.